let's take a look at this problem. We're going to use a rate of change in order to find solution. In this particular case, we're asked about theater. The theater company's profit, P of X, in dollars is described by the equation P of X equals negative 60 times X squared plus 1800 times X plus 1600, plus 16,500, where X is the cost of a ticket in dollars. What ticket price will give the maximum profit? Let's take a moment and think about this question. So remember, when we solve problems like this with functions, I prefer to sketch the coordinate axis right away in order to use it for understanding better. So we have a specific function right here. And we can see that it's clearly a polynomial function of second degree, right? The greatest exponent is 2. Yes, I should remember this topic good because he was the only student in the class. Yes, sir. Remember, while analyzing polynomial functions, we have to look at the degree and the leading coefficient of the polynomial function. Am I right? So here we can see that it's going to be a parabola. Based on the leading coefficient, this parabola should be facing downwards. So before solving, we can make a prediction that our curve would look something like this. I don't know if it's centered or if it's above or below the coordinate axis, but I can assume that the profit should be positive for them, but there are situations where profit of a company could be negative, so it means company is losing money. So I cannot say for sure in which quadrant this function would be. And we're asked where profit would be the maximum value. By looking at this graph, which point do you see as a maximum profit? I can tell you for sure, it's going to be highest point of this graph. For this particular case, this point would be in the vertex because we're working with polynomial function of second degree. When function reaches its absolute maximum, that's where would be the solution for this problem. When will the ticket price will give the maximum profit? Now, what ticket price will give the maximum profit? So it's also important to see that in this point, function changes its direction, right? From increasing to decreasing. Another interesting thing, you see I drew a tangent line to this point, and this is a definition of instantaneous rate of change. Considering that, we can make a statement that in order for us to have a maximum profit, the instantaneous rate of change of this function should be 0 in this point. Do you agree with me? Do you understand my reasoning about it? Yasser, Ahmad, are you with me? Please participate in the class. Okay, I'll treat that as yes, if you understand my reasoning. Calculate the average rate of change in profit for each interval of ticket prices. So, Ahmad, please evaluate the average rate of change for these two intervals, and Yasser will evaluate the rate of change for these two intervals, while I will evaluate the rate of change for other intervals, so we can work together. We have to remember the average rate of change function by heart. So it looks as follows: delta p of x over delta x equals p of x 2 subtract p of x 1 divided by x2 subtract x1. In this particular case, x1 is 12 and x2 is 15. All right? So now I substitute my values in here, and I would have 3 in the denominator, 15 subtract 12. And in the numerator, I'll have these two functions, but evaluated considering x2 and x1. Let me write it down. Minus 60 times x squared, x2, it would be times 15 squared, plus 1800 times 15, plus 16,500, subtract p of x1. Right away, I know that I'm gonna have 16,500 in this function as well, but I'm going to subtract it, so I can say that I'm going to simplify 16,500, and I'll have to subtract only the following terms. Subtract minus 60 times 12 squared, and subtract 1800 times 12, and that's it. Now we just have to calculate this. So 15 times 15 is 225 times 60. It's 13,500. Let me move my solution a little bit farther up so I have more room here. Are you working along with me, guys? Or are you practicing calculating the average rate of change? So minus 60 times 15 squared would be negative 13,500 plus 1,800 times 15 it would be 2,700 plus 2,700. Subtract. So minus negative 60 would give me plus, right? So plus 60 times 12 squared, which is 144. So 60 times 144 would give us 8,640. And finally, subtract 1,800 times 12. $21,600. All this divided by 3. So now I'll group up my terms a little bit. I have negative and negative here and 2 positive values here. So negative 13,500 subtract 21,600 plus 27,000 and wait a second, 1,800 times 15. It's 27,000, yeah. So 27,000 plus 8,640 subtract 13,500 and subtract 21,600. And we left behind was 540 divided by 3. 540 divided by 3. And it gives us 180. So this is an instantaneous rate of change for interval from 12 to $15. X is price of tickets in dollars. So, and profit also described in dollars. But basically profit in this case, as soon as profit is a function of the cost of a ticket, we should say that this is the instantaneous or average rate of change. So profit per dollar. For every dollar we add to the price of a ticket, the profit increases by 180. Is it clear with you guys how to solve this problem? Yasser? Ahmad? So are you solving the following intervals? Look, it's a lot of them, a lot of calculations. I solved the first one for you. Okay, please take a few more minutes and I'll get back to you and we'll analyze your answer, okay? Take 5 more minutes to evaluate this intervals. Okay? Guys? Yasser? Ahmad? If you don't want to use your microphone, you have to type faster. Can you answer me my question? Are you solving for other intervals or not? Okay, please continue. Oh, guys, how are you doing? How far did you get? Guys, so if you see the similarities, everywhere we have second point as 15 seconds, and here we have 15 seconds as the first point. So your calculation should be easy. You have to change only one number in there. No need to calculate everything over and over again. So how far did you get? Ahmad, Yasser, I'm trying to talk to you. Can I continue? Can I move on? So I will evaluate only two more limits as it gets closer to $15 per ticket, 14.8 and 15.2. So I'll replace my 12 with 14.8. Let's use the calculator to do so quickly. So 60, so 14.8 times 14.8 times 60 would be 13,142.4, and 1,800 times 14.8 equals 26,640. Subtract 26,640. Now let's use the calculator to combine all of these terms. So we're going to be 27,000 plus 13,142.4, 40,142, 1,142.4, 4. 13,500. So 40,142. 40,142, 4, subtract 26,000 26,640 and subtract 13,500. And I see that after doing all of these operations, after doing so, move this down here. Here I have plus. By doing so, we can see that this denominator equals to 2.4. Look how smaller it is than the previous number. Before that, we had 500 something. Now we have 2.4. And we can see that the gain in profit per dollar is getting less and less. And this time it's 0.8. Profit per dollar increased. And we can see that on the opposite side, remember, this time we're approaching $15 per ticket here. We're approaching it from left-hand side, right? We're making an average rate of change where the first value to the left from this point. And here we do the average rate of change for the same point, but now we approach it from the right, right? 15.2, little step to the right. And you're gonna see that at this point, our instantaneous and our average rate of change would be negative. So it start losing money. But it will be, again, really small value. What do all the values for the first 4 rate of change calculations have in common? They all have in common that they share same point, right? We approach specific point on the graph. I can estimate that when my price per ticket equals $15, I would have instantaneous rate of change of 0, or my function would take its greatest value, or local maxima, or absolute extrema, maximum profit. It means that this point is the highest point on the curve when the function takes its greatest value. And again, you see they ask us to plot the graph profit function, and the maximum will occur exactly in this point. So now we know that this point is located when x equals 15. X equals 15. This is the point location. Guys, do you understand how we determine the maximum profit? So a general approach is as follows. The average rate of change should be traveling to 0. So it must be getting closer and closer to 0 as we approach this specific point where we would have a maximum value of a polynomial function of second degree. As we approach this point, our average rate of change becoming closer and closer to 0, as well as on the opposite side of this point. So if you take a look at the coordinate axis, and we have point 15 here, and we have point 14.8, and we have point 15.2, right? This is the left and right hand side. And remember, yes, sir, you've been to that class. When we evaluate instantaneous rate of change, we use a shrinking interval in order to do so. And that's exactly the case. We're basically shrinking this interval to this point 15 and getting an instantaneous rate of change. If you evaluate the instantaneous rate of change from 14.8 to 15.2, you would see that it's getting close to 0. Again, this is basically a way of defining the average rate of change, but by getting as close as possible to this point, we shrink this interval as many times as we can, taking smaller and smaller values in order to evaluate the instantaneous rate of change. One of the methods is taking two average rate of changes to the left and right hand side, and they both should travel to 0. Is it clear? Ahmad, Yasser? Okay. Let's reflect on this solution. What is the relationship between the instantaneous rate of change in profit and the cost of a ticket at the point where the maximum profit occurs? What is the relationship between the instantaneous rate of change in profit and the cost of a ticket at the point where the maximum profit occurs? The relationship as follows. As the profit reaches its maximum, the instantaneous rate of change travels to 0. And the price of ticket would be 15 at this point. How do we know that the instantaneous rate traveling to 0? First of all, that the tangent line would be horizontal, which means it has 0-degree angle, right? 0-degree angle, which means the rate of change is 0. How else could you use your graph and your knowledge of rates of change to verify that the maximum occurs at this point? Exactly, we're going to use the tangent line. What would the tangent line look like at the point where a maximum occurs on your graph? The tangent line would be horizontal because it has no slope. It is not changing. Explain how you could use the tangents and rates of change to identify the value where a minimum occurs on a graph. Exactly the same way. Minimum would occur in a point where instantaneous rate of change travels to 0. Average rate of change travels to 0. We take a second line. Basically, if you test it with average rate of change, if you take this 2 points and make a second line, it also would have instantaneous rate of change 0. So for polynomial function of second degree, it would mean that the vertex is in the middle of these 2 points. So right now, we'll take a look at the short YouTube video. I hope you can see my screen now. Here is a short video. You know, this one. Just a second. Subtitles. So we watch this comment, right? This is what we covered when talking about rate of change, right? We show dependence of one variable over another one. This is really important to understand. That's why I repeated in today's class. Change in y to the corresponding change in x. And you can see that on the screen, he's taking a certain segment, right, of this graph. It may be going farther up, but when we're talking about average rate of change, we can take a certain interval, right? When we talk about instantaneous, we talk only 1 point. In this video, you've seen one interesting example of using the rates of change problem. For example, here we've been evaluating the change in surface area of a drop that evaporates. You see, problems could be much more complicated than just car riding on a hill or something. Here is another good video. Let's take a look at it. Sorry. No, sorry, not this one. Oh, and here's one, what I want you to see. It's approximation of an instantaneous rate of change. This is for Ahmad, who missed classes. So now I see he's comparing the average rate of change to instantaneous rate of change. And he's using advanced techniques from calculus, which called derivatives, but we won't get into that just yet. We know another way of estimating the instantaneous rate of change, and that's what we did in today's class. We took a shrinking method where we have certain point on a graph like 15, and we take 2 points that are extremely close to this value, 14.8 or 15.2, and we use them to calculate the average rate of change. We calculate it through the average rate of change formula, and we get the same, pretty much the same result as general formula for instantaneous rate of change. We also have this one formula, but in a bit different way, where we talk in terms of small increase. Remember when we take h, which is a step, and we make the step incredibly small, 0.001, for example, and we evaluate the average rate of change for some function in the following way. We take the FO x plus h, subtract FOX, divided by x minus x plus h minus x, so we have only h left. And Yasser, do you remember this method? We used it in a previous class. So I hope you enjoyed this videos, and let's get back to the textbook. So here is example number 1. Leonard is riding a Ferris wheel. Leonard's elevation h of t in meters above the ground at time t in seconds can be modeled by the function h of t equals 5 cosine 4 times t minus 10 degree plus 6. Show things that Leonard will be closest to the ground at 55 seconds. Do you agree? Support your answer. Again, will be closest to the ground at 55 seconds. So let's think about it. We can see that it's a cosine function. So it will look as follows. As soon as he's riding a Ferris wheel, it models his height above the ground. We had such a problem before. So he would be going something like this, right? Up and down on the Ferris wheel. And the closest to the ground, he would be in the bottom of this curve, right? So we have to find the instantaneous rate of change equals 0 and not in the top, right? Because in the top, it won't be closest to the ground, but in the bottom, in the valley. To find the answer, first of all, whether it's going to be 55 seconds or not, we have to evaluate the approximate rate of change in this period of time. Approximate instantaneous rate of change. Take a look at this problem. So which point in time should we choose to estimate the instantaneous rate of change? I personally would choose 54 seconds and 56 seconds. So I evaluate the average rate of change to the left and right hand side. And then you can see that the instant average rate of change is getting close to 0. Here into negative and here into positive. Okay, so now we can make a conclusion that if from one side the instantaneous rate of change, the average rate of change is negative, it means the graph is going down, right? And in the next moment of time, after we pass this point, we have the same rate of change, which is close to 0, but going up. Do you see what I'm trying to show you here? That this point where graph changing its direction, and in this point, the instantaneous rate of change equals 0, this would be our, for example, in this case, local minimum value, because after this point, function goes up. It's not falling down below this point, it goes up after it. So if my first average rate of change to left-hand side is negative, and second one is positive, it means I was decreasing and then I'm increasing, so it's local minimum. If my average rate of change would be first positive and then negative, it means it's my local maximum. So my function was growing, and after passing this point, it starts to decrease. Is that clear, guys? Please take a look at the solution, note it down into your textbooks. Take up to 10 minutes. So how are you doing, guys? Please note down this is a cosine function. We'll move on in a second. So guys, I hope you had enough time to copy down this solution. Let's take a look at the example number 2. Show that the minimum value for the function happens when x equals -2. So we remember from past classes, we had this method, and I talked about it today, when we add a step to the x, right? We express the step as an h value, and we take this h value extremely small in order to approximate the instantaneous rate of change in the most accurate way. So basically, we are substituting our x value into our average rate of change function, but now we treated x1 and x2 with that x1 equals x2 minus h, or x1 plus h equals x2. So we have this little h step. So our average rate of change function would take a following form. And to estimate the slope of a tangent at x equals -2, we use 2 points in the difference coefficient. For one point, where is x equals -2 and function equals -25, the point where you want the tangent line to be. For the other point, use the general point on the graph of f of x. For example, this general point could be -2 plus h, and the value of the function would be f of -2 plus h. This is what we do in the first step. And we are not substituting h for a very small number right away. You can see that it can be factored and simplified afterwards in some cases. So here you can see that slope equals h eventually. And if we take h small enough, we can say that the slope of a tangent line would be 0. So it means we reach the point of a minimum value for this function. But To show that it's a minimum value, we have to take negative first and then positive, right? Negative 0.1 and positive 0.1. So it means that the function was decreasing before this point and increasing after this point. So this is a minimum value. Minimum value. Is that clear, guys? Since the slope of the tangent is close to 0, there could be a minimum value at x negative 2. And we say it's negative because the left-hand side, we can see that the average rate of change is decreasing, and to the right-hand side, it's increasing from this side, right? If it were the other way around, we would say that it's local maximum. Local maximum. To estimate the slope of a tangent to the curve when x equals negative 2, replace h with small values. When h equals negative 0.01, slope equals negative 0.01. When h equals 0.01, slope equals 0.01. Since the slope of the tangent is close to 0, there could be a minimum value at this point. Take the average of these rates of change to improve your estimate of the instantaneous rate of change at x equals negative 2. And you can see that it in fact equals 0. So use two values of x that are close to negative 2 but on opposite sides of it to calculate values of for the function. Compare these values for the function to the value of x equals negative 2. And we can see that the function takes literally the same value to the left and right hand side. And it's possible only when it's lowest point, so curve going down and then bouncing upwards from it. This is the case when these 2 points would be extremely close to the 0 and they would be equal. Since the slope of a tangent is equal to 0 when x equals negative 2, and since the values of the function when x equals negative 2.1 and x equals negative 1.9 are greater than the value when x equals negative 2, a minimum value occurs at x equals negative 2. Please take a moment to note down this solution because it's really important for your future understanding and studies. This is one of the most convenient methods of solving rate of change problems. Let me know once you finish copying this down, guys, okay? Okay, guys, I believe I gave you enough time to copy down the solution. Let's summarize our today's class. The key ideas. The instantaneous rate of change is 0 at both a maximum point and a minimum point. As a result, the tangent lines drawn at these points will be horizontal lines. I hope it should be clear as a result of today's class. If the instantaneous rate of change is negative before the value where the rate of change is 0 and positive after this value, then a minimum occurs. Graphically, the tangent lines must have a negative slope before the minimum point and a positive slope after. If the instantaneous rate of change is positive before the value where the rate of change is 0 and negative after this value, then the maximum occurs. Graphically, the tangent lines must have a positive slope before the maximum point and a negative slope after. That's what we showed in example number 2 and 1. where we've seen that the rate of change getting to the 0 and changing its sign after crossing this point. Am I right? Please remember these definitions. And let's move on to practicing. So I'll give you a help here. Please start with exercise number 5. Once you finish it, this would be part of your home assignment. So please work on it now. I will write down the formula right here that you're supposed to use for this problem. So for each function, the point given is the maximum or minimum. Use the difference coefficient to verify that the slope of the tangent at this point is 0. Difference coefficient is h. Function for different coefficient when you have delta f of x over delta x equals f of x2, or we know when we use the difference coefficient x2 equals x1 plus h, subtract f of x1 divided by h. Please use this formula to solve problem number 5. Is that clear, guys? Ahmad, Yasser? Ahmad, by the way, I couldn't see you as a participant in a Google Classroom. I only see Yasser and Lareen, but not you. Did you join the Google Classroom? Yasser, Ahmad? Okay, good. So, Ahmad, in case you don't know this formula yet, I wrote it down on the desk. So you can solve this problem number 5 and practice your understanding of rates of change. Please do it right now. Yes. So how is going, guys? Do you have any questions? Is it better like this? So guys, how's doing? So guys, how how far did you get? A, B, C, D? Okay, guys. I'm going to solve one example with you together. I'm gonna solve B, just an example. So we have the rate of change formula. And now let's implement this formula for question B. So f of x1 plus h, x1 in this case is 0.5. So I'll write it down as negative 6 times 0.5 plus h squared plus 6 times 0.5 plus h plus 9. Subtract f of x1 and it's 10.5. Subtract 10.5. All of this divided by h. Now let's open the brackets. This is a complete square formula. We're gonna have negative 6 times 0.25 plus h squared plus 6 times 0.5 plus h. We can open these brackets right away. We're gonna have plus 3 plus 6h plus 9 minus 10.5 divided by h altogether. You want to shrink it a little bit? Squared here, plus 3 plus 6h plus 9 minus 10.5. Let's open up these brackets. You're gonna have 6 times 25 is gonna be 0. It's gonna be 1.5 plus h plus 6h 1.5 plus 6h plus 6h squared plus 3 plus 6h. Oh, by the way, it's negative, right? Multiple is negative, so we're gonna have negative 1.5 negative 6h and negative 6h squared plus 3 plus 6h plus 9 minus 10.5 divided by h. I'll clear the beginning, move on here, move on here, continue my solution here. So negative 1.5, let's group up the terms. Negative 1.5 plus 3 plus 9 plus 10.5, negative 10.5. So it's going to be 9 plus 3 is 12, and 10.5 plus 1.5 is 12. So they turning into 0. We can cross them out. So we left behind with terms that have h in it. Negative 6h and plus 6h. Gonna cross them out as well because they're getting simplified. And everything we're left behind is 6h squared. If we simplify it, we get 6h. And if we take h, really close number to 0, like 0.1 or negative 0.001, we can see that the rate of change traveling to 0. So this point could be local. Yeah, so at this point, the slope of the tangent line could be 0. And now let's start to define whether it's maximum or minimum point. We define that tangent line is truly traveling to 0, right? But what about whether it's maximum or minimum? First of all, I can see that to the left-hand side, so to the negative values of h, my slope is negative. For positive values of h, my slope is positive. So I can make a statement that it was local minimum, the lowest point. As soon as rate of change was negative, became positive. And also I can take a look at the leading coefficient of this polynomial function. This is part of our next unit. We already covered it in one class, and we're going to continue it after writing the unit test for this part. Do you agree with my solution, guys, on question B? Do you have any more questions for today? Yes, sir, great. Do you agree with me in my solution for B? Did you do it on your own? Okay, so guys, please keep in mind that in the next class, we're going to have a unit test. Please repeat all the problems from this unit regarding average rate of change, instantaneous rate of change, methods on defining the instantaneous rate of change, how do we approximate it, as well as properties of rates of change that we need to know in order to